for 2-3 minutes.
Sounds good.
It's supposed to get hotter actually over the next couple of days.
Oh yeah.
Are you here at all past today, or are you flying right?
I'm flying back tomorrow.
Okay.
But I'm sure it'll be, however hot it is here, I'm sure it'll be hotter in New York. So.
That's probably true. Yes. It's been pretty nice actually overall. The temperature was hot, but not crazy hot.
Right.
High 20s.
Nice. Good.
All right, so thanks everyone for joining us today. I hope you all had a great week. Today we have the pleasure to host Taylor, who is a postdoctoral researcher at MSR New York, and he'll be sharing with us some thoughts on evaluating, understanding, and improving approaches for machine learning reasoning. So before handing the mic over to you, Taylor, let me remind you all of some house rules. As usual, clarification questions will be allowed to be asked during the talk. For people in person, you just have to raise your hand and wait for me to give you the mic so that people online can hear you. And for people online, you just have to type the word question, or I have a question in the chat, and when the time is right, I'll let you directly ask it. There'll also be some additional time at the end of the talk for people to ask further questions, make some comments, or have a more informal discussion with Taylor. That's pretty much it for me. So whenever you're ready, Taylor, the floor is yours.
Awesome. Sounds good. Well, hi, everybody. It's good to be here. So the plan is basically to talk about how we can build systems with more human-like reasoning, to what extent maybe AI systems already are displaying signs of human-like reasoning, how they're doing it, and how we might sort of improve them further. So the talk is basically divided into 3 sections. So first, I'm going to address this question of, as I said, to what extent do large-scale AI systems maybe already show some capacity for reasoning? And here I'm going to make an effort to distinguish between different types of reasoning. And I'll essentially argue that these systems are, I think, already quite strong in some forms of reasoning, but have major weaknesses in other areas. Then I'll address the question of, to the extent that these systems are capable of some kind of genuine reasoning, what are the mechanisms that allow them to do that, and how does that relate to the mechanisms of human reasoning? And then finally, I'll talk about what I think is maybe still missing from these systems, and how I think we can build systems with more human-like reasoning abilities. But so first, I want to just say a bit about my background and how that sort of informs the overall approach that I take. So my background is originally in cognitive neuroscience, studying the computational mechanisms that support cognitive processes like attention and metacognition, and how those mechanisms are instantiated in the brain. But over the past 5 years or so, I've really been focused on AI and machine learning research, and especially on the potential for sort of synergistic interactions between these 2 fields. And so I think these 2 fields have a lot to offer each other. Just to give a sense of the sort of modes of interaction that I see as being particularly fruitful and that have guided my own work. First, I think cognitive science and neuroscience has a lot to contribute in terms of evaluation methods and analysis methods, and sort of like a taxonomy of different cognitive capacities that I think can be useful in trying to more precisely evaluate what the strengths and weaknesses of current systems are. But I also think cognitive science is a sort of a rich source of theoretical insights and hypotheses that can be a guide both for trying to understand what are the learned mechanisms that maybe emerge in current large-scale AI systems, but also I think can offer sort of high-level inspiration for how to further improve those systems. And so, I certainly don't think that cognitive neuroscience can just like directly give us the answer for how to build a more human-like system, but I think that insights from cognitive science can sort of suggest promising directions for how to think about certain problems. But right, so as I said, it's certainly not the case that I think cognitive science has like a fully formed answer for how to build intelligent systems. And in fact, I would go so far as to say that many of the problems of cognitive science and neuroscience, I think are really problems that can be very fruitfully addressed by directly doing machine learning research. And so this includes, of course, the development of novel algorithms with increasingly general cognitive capacities. I think increasingly it's possible to view these as sort of like model systems that we can study empirically, similar to how neuroscientists study the brains of other organisms. And finally, I think machine learning research offers an opportunity to test general principles of cognition. In other words, I kind of think of the broadest ambitions of cognitive science as being to sort of try and identify general principles of intelligent systems, whether those be biological or artificial. And so I really see progress in AI as fundamental to understanding the brain and cognition. And that's really what's motivated much of my recent work and the work that I'm going to discuss today. Okay, so as I said in the beginning, I'm going to start by addressing the question of the extent to which current AI systems are maybe already capable of some degree of human-like reasoning. So I'm sure I don't have to apprise this group of the debates surrounding large language models. Suffice it to say, this is an area with an enormous amount of disagreement, with some folks, sort of pointing to the surprising capabilities of these systems and suggesting maybe this is like, a few steps away from AGI, and others arguing, it's all an illusion. This is all just mimicry of their training data. So I'm not going to align exactly with either of these views. But I think the first point I want to make is that I think really this question isn't specific enough. And I think if we take a cognitive science perspective here, we typically don't think of reasoning as some kind of monolithic unitary process, but instead we tend to make distinctions between different types of reasoning and different types of cognitive processes. And so I think it's important when studying these systems to try and be precise about the specific type of reasoning that we're talking about. And so basically what I want to argue first is that I think current systems are actually quite good at some of these things, but in a way that can sort of interact with some of these other processes where they have more weaknesses. And in particular, I'm going to present some work that suggests that I think current LLMs are already quite good at analogical reasoning, but in a way that interacts with much weaker abilities with some of these other processes, including especially physical reasoning and mathematical reasoning. And so analogical reasoning is, of course, a central part of human reasoning. This is essentially the process of sort of making an abstract comparison between two potentially very different sorts of things. So just one example comes from this potential comparison of language models and stochastic parrots. Here we have two very different sorts of things, AI systems and birds. But despite those superficial differences, we can often identify more abstract correspondences that allow us to sort of usefully solve new problems. And so the perspective from cognitive science is that this ability for sort of abstract comparison is really central to our ability to make sense of new problems and new environments. And so in this paper that we published last year, we were interested in the question of whether large language models might have a kind of emergent capacity for this kind of analogical reasoning. And so we performed essentially sort of comprehensive evaluation, focusing on GPT-3 and GPT-4 across a number of different text-based analogy domains. Most notably, this included this matrix reasoning task, which was based on a task called Raven's progressive matrices. You might be familiar with. Basically, this is sort of considered as maybe like the gold standard of tests of analogical reasoning. It's an abstract problem-solving task with sort of patterns of geometric figures, and you have to figure out what the pattern is and use that to fill in the blank. So what we did here, though, is we created essentially a text-based version of these problems. And this served two purposes. First of all, at the time we did this, we didn't have access to the vision system, so it was only text-based. But I think maybe more substantively, this effectively created, I would say, a new task that we could be fairly confident wouldn't be in the model's training data. And so it's really evaluating this kind of zero-shot reasoning that we think of as being central to analogy and abstract reasoning. Right, and so using this setup, we can basically recreate all of the standard problem types that are found in these Raven's matrices problems, but here in a text-based format. And essentially what we found is that GPT-3 was, I would say, shockingly good at solving these problems, better than the average level of human performance. So this is comparing GPT-3 and a group of college students trying to solve the same types of problems across different problem types. And so at this time, I was extremely surprised by these results and sort of followed them up by doing more experiments using essentially all of the major sort of text-based analogy types that I could come up with. And GPT-3 performed really well on these other problem types as well. The one exception being these story analogy problems where GPT-3 didn't do quite as well, but here GPT-4 performed much better. And this GPT-4 came out like right around the time that we were sort of doing revisions for this paper, sort of closed the gap on this last problem set here. And so overall, these results suggest that I think at least for sort of text-based problems, text-based analogy problems, GPT-3 and GPT-4 have very strong zero-shot performance, essentially on par with human reasoners, and subsequent work from other groups with other systems like Claude especially has shown even stronger performance than these systems. But so just going back to this point about these different types of reasoning, these results, I think, speak specifically to the analogical reasoning abilities of these systems. But there are lots of results to suggest that LLMs are quite bad at some of these other types of reasoning. And of course, it's possible to create problems where different types of reasoning interact with each other. And when you do that, you can get a situation where these systems are able to sort of carry out the analogical processes that are involved in the task, but can't ultimately solve the problem due to deficiencies in some of these other types of reasoning. So one example of this comes from some problems we looked at in the same paper, where we were looking at the ability to use analogies to solve a physical reasoning task. This particular, yes, yeah. During is great, yeah.
So just a very quick one related to the results you were showing us right before. Mm-hmm. Is there any risk whatsoever that some of these tests were available on the data that has been used to train the LLM, so that some exposure is there? And would that in any way influence the performance? Or would you say it's safe to say that nothing out there in the training, because obviously some of these tests are standard tests, so there might be material out there on the net?
Yeah, so it's sort of a mix of different answers to that question. So for the matrix reasoning task, which is where we started, this is not only a data set that we created from scratch, but like a task that we invented for these purposes. So that was kind of the first result that really got my attention and made me think that there's no way you could explain this as just like, brute force copying of the training data. The letter string analogies we also created from scratch. There are also letter string analogies on the internet. Hard to say, how much that affects their performance. These verbal analogies and story analogies are data sets that existed before, but they seem to only be on the internet and like sort of attachments that you have to download. It's not clear how likely that is. It's going to make it into the training data. So, it's hard to say overall, but I think it's certainly not the case that you could explain like all of the results as just some sort of mimicry of the training data. There is a sort of broader issue, which is like not literally these problems being in the training data, but similar problems. And so many people have suggested that this is, maybe just interpolation to similar problems. I'm not even sure I disagree with that necessarily. It's hard to say, how we would even sort of quantify or evaluate that. But if we're in a situation where like mere interpolation is producing this kind of results on totally new tasks that we invent, I think that's like pretty stunning, essentially. So
is there a difference between interpolation and that you're talking about and like analogical reasoning? Because I feel like there's similar concepts.
Yeah, I mean, I think the sort of perspective from cognitive science is that analogical reasoning is like some extreme form of extrapolation. Basically, it's like zero-shot extrapolation to a totally different task. But here we're talking about interpolation across totally general purpose, anything you can see on the internet. So maybe it's interpolation with respect to that, but it seems to support what would appear to be human-like extrapolation to even like a new task that we invent. But yeah, I mean, I think these are like totally persistent issues that I think are arguably going to be best addressed by open source language models, where we can not only have access to the weights, but have access to the training data as well. And people are starting to develop those systems. So I think these are important questions, and it's something that I'm interested in sort of pushing further. Yeah.
I see that for story analogy, the gap between machine and human performance is the least. In fact, human performance is, I guess, maybe a tiny bit better than machine performance, whereas for the previous tasks, it was quite different. Human performance was much lower. So I wonder if within these tasks, there is sort of like a hierarchy or like a distinction between some type of tasks are more human friendly and, some type of tasks which, for example, doing calculations, right? We have a calculator for a reason. We cannot calculate, but these machines are essentially calculators. They can do that, right?
Right.
So do you have any thoughts on that?
Yeah, I think there are a lot of factors that might explain the differences here. One is what you identified, like people in general just tend to do better with semantically meaningful content, stories, things that are meaningful. This is like one of the most classic results in psychology. So it's not surprising to me that they're doing better at story analogies than they are at this like totally abstract matrix reasoning task. I think another factor probably is the more sort of high dimensional the problem is, I think the more challenging it is for language models. So in the case of the matrix reasoning tasks, basically there's a very strong correspondence between what a token is and what the relevant like sort of unit of analysis is in the problem. Like tokens are basically digits, those are the objects in the task, right? Whereas in a story, you have a bunch of words and you need to sort of boil it down to some more low dimensional representation. So I think that's probably also going on here. Later on, I'm going to talk about how sort of multimodal models are doing on visual versions of these tasks, and they're doing very poorly. And I think there it's like kind of an extreme version of this high dimensional problem of trying to extract some low dimensional representation to operate over.
I'm wondering. Oh, right. Sorry, Mike.
I'm wondering how consistent individual humans were on these tasks. So like, because I'm assuming each point here is an individual data point from an individual person. So are there people who are just like properly sub GPT and others who are super GPT, as it were, or is it kind of noisy for each individual?
That's a good question. I mean, we didn't do like test retest. Test someone on a good day, test someone on a bad day. There's probably variance amongst individuals. I guess the one thing to note is that, you see there's a distribution here of people.
Quite wide, actually.
Quite wide. And in fact, like the matrix reasoning tasks, there's one person who got everything correct, right? Yeah. So, I guess.
And in letter string analogies, one person who got nothing correct.
Right, yeah. So yeah, there's a distribution of human performance. So, I don't want to, that makes it complicated to make claims about language models being better than people and that. So I wouldn't make that sort of claim based on these results. I would just say it's like in the range of what people are capable of, right?
Cool. Yeah, thanks.
Okay, right. So so moving on to these other reasoning domains and the ways in which they interact with analogies sometimes. So here we were looking at this physical reasoning task. This actually came from a study that was done with children. But basically, the way the task works is you're seated at a table with a bowl of gumballs in front of you, and your task is essentially to try and transfer those gumballs to another bowl across the table that's out of reach, using some assortment of miscellaneous tools. And the sort of point of the original study here was that before solving the problem, the children were presented with an analogous story involving a genie who lives in a bottle and has recently moved to a new bottle and wants to transfer his jewels to the new bottle. And the basic finding is that depending on, there are different versions of the story, and depending on the solution that's identified in the story, children sort of tended to identify an analogous solution to the physical problem-solving task. So this is kind of a classic case where people, even at a very young age, are using analogy to solve some problem that's otherwise kind of difficult for them. And so the interesting finding here is that we found that language models, so we described the story, described the task. Language models are typically pretty good at identifying the relevant analogy here. So they can tell you like which item in the story, which characters in the story are analogous to which items in the task. But when you actually ask them to use that analogy to solve the task, they tend to propose basically very elaborate but essentially nonsensical solutions. So I won't walk through in detail this solution, but I really tried to make sense of it, and it's just completely nonsensical. And I think basically what this reveals is, I think, a kind of a basic lack of physical understanding. And so the point here isn't that this is like some fundamental limitation of LLMs. I think who knows whether this sort of capacity will emerge with more training data. But the point is that I think a lot of tasks involve sort of interactions between different types of reasoning processes, and I think it's important to try and pull those apart when we're evaluating what these systems are good at. Just to give another example of this, there have recently been a few studies looking at variants of these letter string analogy problems that use a shuffled alphabet, and the basic finding here is that language models seem to be worse at the problems with the shuffled alphabet than they are at problems with the standard alphabets. But one thing to notice here is that these particular problems require essentially a kind of indexing operation where you have to basically convert letters into their position in this list. And this sort of indexing or counting operation is something that language models are notoriously bad at. And this essentially raises the question of, whether poor performance on this task reflects some general difficulty with analogy or just some specific problem with counting or indexing. And it turns out if you use a version of GPT-4 that has access to this code execution capacity, which it can use which it does use to perform this indexing operation, then it's able essentially to correctly identify the intervals in the list, and then it can solve the problems again roughly at human level. And again, the point here isn't that I think this code augmented version of GPT-4 is like important for analogical reasoning somehow. The point is that I think analogy is dependent on having strong representations of whatever domain you're making analogies about in the first place. And if those representations depend on other reasoning processes that language models have weaknesses in, you might get a kind of confusing pattern of results where it's not clear which process it's having trouble with. And so, yeah, so I think this is all just to say I think it's important to try and tease apart these different cognitive processes. And I think this is an area where I think cognitive science can be a useful guide. Okay, so one question that arises from these results is, for the capacities that these systems seem to be strong at, especially in the case of analogical reasoning, what are the actual mechanisms that they're using to solve these problems, and how does that relate to the sort of putative mechanisms that humans use to solve these problems? And here I think it's useful to actually look at sort of previously proposed modeling approaches in cognitive science that have been proposed for thinking about analogy, and also some previous research in deep learning focused on similar sorts of problems. So Arguably, the kind of like canonical cognitive model of analogy is this structure mapping approach of Daedric-Gintner. And this approach, you basically have sort of structured propositional representations involving entities and relations. So this is a classic example involving an analogy between the concept of flow of liquids and heat transfer. And essentially the sort of core process of analogical reasoning, according to this model and basically every other cognitive model of analogy, is the process of analogical mapping. And analogical mapping is basically a process of identifying which elements in one situation go with which elements in the other situation, based both on the similarity of those elements and especially based on the similarity of their relations. And so this is sort of the classic cognitive picture of how people solve analogies. On its face, this looks maybe quite far away from the world of neural networks. It's not clear how you're going to implement these kind of structured symbolic representations and routines in a neural system. But there are actually more recent cognitive modeling approaches, including some work that I've been involved in, that essentially try to take some of the high-level ideas of this structure mapping approach and kind of convert them into the world of vectors and gradient descent. So in this particular approach that we call probabilistic analogical mapping, rather than having sort of structured symbolic representations, here instead you have attributed graph representations where the nodes represent entities, the edges represent relations, and each of these nodes and edges has vectors assigned to them. You can get these from word embeddings, computer vision systems, for instance. And then analogical mapping is performed here essentially by optimizing a kind of similarity-based objective just using gradient descent. And so this approach is capable of the same kind of zero-shot analogical reasoning you have in classic cognitive models, but here in a way that uses representations that are derived from real-world data as opposed to just sort of hand-coded symbolic representations. And so this, I think, maybe starts to move closer to the world of neural networks. But the question is, how might a neural network actually implement this essentially graph matching procedure? And importantly, are there any inductive biases that can kind of encourage a neural network to solve problems using this kind of graph matching approach? And it turns out there's actually been a lot of work over the past few years, including work done here at Mila, essentially looking at inductive biases that encourage neural networks to perform more explicit relational processing. And this, I think, turns out to be both very closely related to the classic cognitive models I was just talking about, but also I think is maybe suggestive of how large language models are solving these problems. So just to walk through an example of one of these architectures, this is an architecture that we refer to as the emergent symbol binding network. It was kind of inspired by the concept of abstract variable binding in cognitive science. Basically, the way it works is you have separate perceptual and control pathways. You have a perceptual pathway with some neural network encoder. You have a control pathway with a recurrent controller. And these pathways essentially only interact through an attention operation involving this external memory, where basically the current perceptual embedding is compared to the perceptual embeddings in memory, and the corresponding control embeddings are then retrieved based on that pattern of similarity. And so there's basically a separation of the perceptual and control pathways here, such that the control pathway essentially only has access to information about patterns of similarity over the perceptual embeddings rather than the sort of content of the perceptual embeddings themselves. I think in more recent work, this inductive bias was made even more explicit. This is work from here at Mila, where rather than using recurrent networks and an external memory, instead this entire process sort of converted into a parallelized feed-forward architecture that now explicitly computes this matrix of similarities over these perceptual inputs and then passes that on for downstream processing. And so both of these architectures are extremely good at learning relational tasks. This is just one example with an identity rules task. It's kind of simplified matrix reasoning task. And here, the emergent symbol binding network, this ESBN model, was able to learn this task much faster than a number of baselines. but importantly was able to sort of extrapolate any rules it learned out of distribution to completely novel objects in a way that these other architectures didn't seem to be able to. And so, this is generally the pattern that you see with both of these models across a range of different abstract relational tasks. And I think the CoRelNet model actually performed better than this ESBN model. Right, but so, the important point here is that both of these architectures depend on essentially the separation between perception and downstream reasoning, where the downstream reasoning processes have access only to information about these sort of patterns of similarity over the perceptual inputs. And this is really exactly the information that is sort of at the heart of these cognitive models of analogy. So there's a sense that you're biasing neural networks to process their inputs in terms of patterns of similarity is kind of encouraging this analogical mode of processing. The question then is, what exactly does this have to do with language models? Well, it turns out that the same inductive bias can be implemented in a transformer-like model using a relational version of attention. So in this recent work, we introduced this architecture that we called an abstractor, which uses a relational form of attention. And basically, this is like exactly the same as standard self-attention, but here the values are essentially a separate set of learned representations, that aren't conditioned on the input in the way that standard self-attention is. And so this gives you essentially the same degree of abstraction that you get in the other two relational architectures that I mentioned. So just some of the results from that work. This is just showing this abstractor model learning various relational tasks, sorting tasks, also more complicated mathematical reasoning tasks faster than a transformer baseline. And so this captures the same kind of sample efficiency that we saw in the other models. But I think this also offers essentially a hypothesis about the kind of emergent mechanisms that might drive this kind of reasoning in language models. So the basic idea is, this architecture is basically a special case of transformers. It's a transformer that's biased to process inputs only in terms of relations. But I think, given that this is a special case essentially of transformers, I think it seems plausible that this sort of circuit might essentially emerge in language models, given sort of massive scale of their training data. And if that's the case, I think that would suggest that maybe at some level there's in some sense a deep connection between how language models are solving these problems and the sort of traditional models we have in cognitive science, and maybe how we think that people are actually solving analogy problems. But so this is, of course, just a hypothesis. I think one of the things that I'm really excited to pursue in future work is basically mechanistic interpretability research, essentially sort of studying the internal mechanisms of these systems, basically like a neuroscientist would study the brain. Right, yeah.
Can I just ask about that abstractor model again?
Yeah.
I want to understand the details a bit more there. Yeah, here, thank
Yeah.
you. So, like the paper we did, the Kurg et al. Paper,
Yeah.
you're constructing a set of relationships. Are those relationships between the keys and the queries, basically,
Yeah.
that you're driving from those inputs? Okay, got it. And then you've got a set, so then the values, those are learnable vectors.
Mhm.
Okay. And so then you just run standard self-attention, but with these learnable values.
Exactly, yeah.
And the relations are just used to derive the attention weights. That's it, as normal?
Just to remix the values just as normal, yeah.
Okay. Okay.
Basically, another way to think
Interesting.
about it is like cross attention, but you're just swapping like where the keys and the query. So rather than having queries come from a decoder, keys and values coming from the encoder, now we have values in the decoder, keys and queries in the encoder.
Okay,
Yeah.
got it. And can you just give a little bit more intuition for why this helps with abstract reasoning? Because, okay, so because the relational structure that you've got here is to some extent what's always done with self-attention anyway, right? You do the comparison of the key and query and determine your attention weights. So why do the learnable values help with abstract reasoning?
Well, the learnable values, it's not the learnable values that help, it's sort of isolation of the values from the perceptual inputs themselves. So now, so just in the same way that the CorelNet, the Kurgadal model, is only passing on this information about basically inner products between perceptual inputs. Here, the only thing that you're going to get in the output of this attention operation is basically, the values sort of remixed by these inner products, which are very well suited to representing relations.
I see. Okay, so the key point is that the actual content that you're going to pass through the layers of your neural network is not determined by the perceptual inputs, in fact, and that's what helps with the abstraction.
Yeah.
Okay.
And also, I should note in much more recent work, turns out if you sort of interleave this sort of layer with standard self layers, so you're not like literally bottlenecking it so that the perceptual information can't go on, but you're just giving it this circuit that's sort of more predisposed to focusing on relational patterns. Even that can help quite a lot relative to standard transformers. You don't have to like literally cut off the perceptual information in order to get very similar benefit.
Okay, interesting. Thanks.
Taylor, I have another question related to Blake's. So one thing that I find strange here is the values. They're learned, but is there like one value vector for each of the inputs?
Yes. Yeah. Exactly. There has to be a corresponding.
So that only makes sense if the inputs have a fixed meaning, like some sort of fixed structure input. But if you think about transformers taking sequences in input, then the meaning is always different, right? So how could that work in that case? It doesn't make sense to me.
So there are actually two methods that we explored in this paper for defining the values. One is just positional, basically. So either learned positional or fixed positional codes. So in that case, the values just represent the positions. That might seem kind of specific. I do think space seems to be like a really useful way of organizing relations. So there's a lot of tasks that you can solve that way. Another mechanism that we explored is basically a clustering mechanism where you have some sort of set of learned clusters that these vectors correspond to. And you basically sort of, this is in a way a kind of weakening of this division between perception and relations, but you basically sort of assign each of these perceptual inputs to their closest cluster in some sort of reweighted version of the perceptual inputs, and then that's the cluster that you use for the values. So there are different ways that you can assign these values, but the basic idea is to try to have some sort of division where they're not just like literally conditioned on the inputs.
Right. Okay, thanks.
Right. So so this is the abstractor architecture. These sorts of architectures are great at learning relations and generalizing them, but I think also I think it's suggestive of how transformers might solve the same sort of problem given much larger scale of training data. And that's something I'm interested in focusing on future work. Yeah.
So is your idea that somewhere like higher up in the transformer, there's going to be like the values would represent some kind of concepts, and that the transformer would like mix them the same way your architecture mixes your learned values?
That's the idea. Yeah.
And like this interpretability thing that you want to do, like, do you have tasks in mind? Like, because people have done a lot of work on interpretability on a lot of tasks, and you can see a lot of probably mechanisms that look like analogy. I don't know. I'm curious if, informed from what is already been done in interpretability, you want to try other tasks, or if you want to interpret what has already been done.
Right. Yeah, there has been a lot of work already in interpretability that is, I think, very closely related to this. Two lines of work in particular. There's this work on function vectors or task vectors. And that basically I think of as being like a kind of explicit relational representation that from a sort of cognitive model of analogy perspective, that's basically an input to analogical reasoning. You have to have some explicit representation of relations over which you're doing this kind of similarity-based reasoning. I think maybe the thing that gets closest to this kind of similarity-based reasoning circuit is induction heads. So, induction heads are like a very simple mechanism for reasoning based on pattern of similarity. Basically, just find the most similar thing that happened before and predict that whatever happened after it comes next. So that's almost kind of like a baby version of analogy, but it doesn't really get you an analogical mapping routine where you have two situations and you're saying which thing in one situation goes with the other. They're not necessarily going to be in this like fixed positional order. And basically, this abstractor circuit essentially computes a mapping just by default. That's what it does. And so, the hypothesis is that you might have something like abstraction heads or abstractor heads somewhere in these language models, just in the way that you seem to have induction heads and other sorts of mechanisms as well. Awesome. Right. So I've addressed, what I think some of the strengths and weaknesses are for current AI systems, emphasizing especially their strengths in analogy and relational reasoning. I've suggested, I think, some of the mechanisms that I think might be responsible for those capacities. But just in the final time here, I want to say a little bit about how I think we can improve those reasoning abilities and the kind of directions that I've been pursuing along those lines. So so I hinted at this a bit earlier, but I've been talking a lot about the abstract reasoning capabilities of language models for text-based tasks, but I haven't said much about how the sort of more recent set of multimodal models perform on similar sorts of visual tasks. So I'm sure many of you have heard of this abstraction and reasoning corpus, or the ARC task from Francois Chollet. This is basically abstract visual reasoning benchmark. It's kind of it's very similar to matrix reasoning tasks. And it turns out that despite the sort of surface level similarity of this task to the text-based reasoning tasks that language models seem to do really well at, the multimodal models, at least so far, seem to be performing well below the level of human performance. So these are just some results from Melanie Mitchell, looking at the multimodal version of GPT-4 performance on the ARC task. This is actually, there's been some discussion of like, are the ARC tasks maybe too difficult, compared to human performance? This is on a simpler set of problems that humans perform nearly perfectly. And here, GPT-4V is just completely failing to solve most of the problems. That's a good question. I mean, I would probably attribute that to just noise. So the question is, what's going on here, and how is this different than the text-based case? Well, it turns out, in my view, I think this isn't really a problem with visual reasoning per se. I think this is maybe a more fundamental difficulty with just basic visual processing of multi-object scenes. And I think this is actually very closely related to a problem that was identified in cognitive science a long time ago, which is referred to as the binding problem. And the binding problem basically arises anytime you want to represent multiple entities using a shared set of representational codes. So let's say, for instance, you want to represent this multi-object scene using codes for different shapes and for different colors, essentially a compositional representation, which is a very useful way to represent images. Well, unless you have some mechanism for basically dynamically binding these sort of shared features together and keeping track of which entity goes with which of these features, you're going to end up essentially with what are called illusory conjunctions, or sort of confusing which features go together with which entities. And this is a problem that seems to arise in human visual processing, particularly when people have to make judgments really fast, based only on a single fixation, and aren't allowed to sort of individually fixate all of the objects in a scene. And so we have a preprint that should be up soon, where we found basically that multimodal models seem to suffer from many of the same problems that people suffer from when they're forced to make visual judgments very quickly and have to use this sort of feed-forward parallel processing. So one simple example of this comes from this simple counting task. So multimodal models are terrible at counting. But interestingly, they're terrible at counting in a way that seems to be, very closely related to the way that people are terrible at counting when you just have to make a judgment immediately without being able to individually enumerate the objects. So specifically, they seem to be able to do this task with high accuracy up to about 5 objects in a scene, but fall apart after that. And this is basically the same range that people seem to be able to do this task when they do it rapidly. They also struggle with visual search, but again, they struggle with visual search in a way that seems to be very specifically related to the way that people struggle with visual search when they have to make rapid judgments. And so there's a classic set of tasks involving 2 different types of search. One where you're just looking for just an individual feature, like find any object that's red, and another where you have to look for a particular conjunction of features, like look specifically for a green T in this image in the middle here. And basically, sort of pattern from psychological studies is people seem to be able to do this simpler disjunctive search very rapidly and extremely precisely, regardless of how many objects you present them with. But when they try to do this sort of conjunctive search task that relies crucially on binding features together, then they seem to need to sort of sequentially search through each of the objects in the scene to find something. And so their performance essentially falls apart as you force them to make judgments faster and faster. And so this is showing essentially the performance of GPT-4V on these same sorts of problems. We see essentially the same pattern where they're able to do the disjunctive search task regardless of how many objects there are, but the performance on the conjunctive search task is a function of the number of objects. And so this again suggests that they have this problem that looks very much like the classic binding problem in psychology. So what's the solution? Well, in human vision, the solution is basically to sort of sequentially focus on individual objects one at a time. But I think more broadly, what's needed here, I think, is basically mechanisms for sort of object-centric processing of visual scenes. So you can think about, what's like the major difference between these digit matrices and this abstraction and reasoning corpus. Well, as I was mentioning earlier, basically in the digit matrices, you already have objects given to you. Basically, the tokens are objects, whereas in the case of the image problems, you have to sort of convert these high-dimensional inputs of pixels or image patches into sort of object-focused representations. And so I'm sure many of you are familiar with sort of methods for object-centric processing that have been proposed over the last few years, including slot attention. But the basic idea is to try to build an inductive bias for sort of decomposing high-dimensional inputs into some set of latent representations. And if you do this in a certain way, these seem to sort of naturally correspond to what we would consider to be objects, meaningful objects in a scene. And so in some recent work, we've been exploring ways to apply these object-centric methods to visual reasoning problems. In one paper from last year, we found that if you just very simply combine slot attention with a transformer, this actually already gave you state-of-the-art performance on these very complicated multi-object visual reasoning tasks. And then in subsequent work, we found that you can do even better if you basically combine the object-centric inductive biases with the relational inductive biases that I was mentioning before. And so this slot abstractor architecture seems to perform especially well on these abstract reasoning tasks, and especially in the sort of out-of-distribution regimes that are probably the most challenging aspects of these benchmarks. But so all of this work has basically been focused on this sort of paradigm of training and testing on individual tasks. And so something that I think is going to be important for future work is either to try and scale these models to more general purpose sources of data, or to try and find some way to essentially align or combine them with pre-trained models, essentially trying to sort of capitalize on the very broad general purpose knowledge that we have in these models that seems to be useful for reasoning, but combine them with sort of more precise object-focused representations. And so that's one direction I think is especially promising. And the other direction that I'm especially interested in these days has to do with another major limitation of current systems, which is that they're particularly bad at what we might call goal-directed planning. So this is just showing recent results from a recent paper from Ida Mominajad, essentially evaluating language models on a graph traversal task, where a particular graph is described to a model and they have to, for instance, try to navigate to a particular location. And the basic finding is that pretty much all current language models are really bad at this task, except for like the simplest graphs. And even then, only GPT-4 seemed to be able to really reliably solve those problems. And what I found really interesting in this particular paper is that language models often seem to make mistakes that were kind of incoherent or seem to contradict knowledge that they seem to understand on some level. So, for instance, you often see in these sort of graph traversal tasks, language models proposing to try to take paths that don't actually exist in the graph that's been described to them. But then you ask them, to describe the graph, like tell me all of the nodes that connect to each other, and they can do that very accurately. And so I think what it suggests basically is that these systems maybe already have a lot of the knowledge and skills that they need to solve these kinds of tasks. And they just need to somehow be better orchestrated or coordinated in the service of a particular goal. And so with sort of that goal in mind, I've recently been working together with Ida and some other folks at MSR to try and build basically modular architectures involving multiple sort of specialized instances of language models. So for instance, you might have one language model that sort of proposes actions, another that monitors those actions and sort of checks them against various constraints. You can build in a search loop and other sorts of sort of modular processes. The basic idea is to try to allow these language models to focus on tasks that they are pretty good at in isolation, and then have a plan sort of emerge through the recurrent interaction of these different modules. In this case, we actually took inspiration from the brain, and in particular the prefrontal cortex, which seems to have specialized subregions for many of these component processes. Yeah.
So I just want to clarify, in part to refresh my memory of this paper and for the sake of everyone else. So each of these boxes here is an LLM.
Yeah.
And what I forget is, do you fine tune the LLMs for these tasks, or are they just done zero shot?
This is done zero shot just through prompting. Currently, we're working on fine tuning specialized, actually smaller language models to try and make it more efficient.
Got it. Okay.
I assume that'll be more effective, but even just with prompting, it can get you very far.
So the specialization is purely through prompting at this point, right?
Exactly.
Okay, thanks.
Right. So this modular approach seems to significantly boost performance on various planning tasks. This is showing results for this Tower of Hanoi task. It's this kind of classic symbolic planning domain. And here you can see that the modular approach, it's called LLM PFC, inspired by the prefrontal cortex, is outperforming various baselines. We also had ablations, looking at ablating different modules in the architecture. And we also saw similar results across a number of the tasks from the graph traversal benchmark that I was just discussing. But so the point here, I think, is really that, again, these systems really already seem to have much of the knowledge that they need to perform planning. And I think what's really needed is just to find better ways to coordinate or orchestrate those skills in the service of a goal. And so that's one of the directions that I think is really promising and that I'm planning to focus on moving forward. Okay, so just to sum up here, first, I think, as we saw in the evaluations of language models on various reasoning tasks, I think LLMs are arguably already starting to show signs of what I would consider to be genuine reasoning, especially in the case of analogical reasoning. And I think this is plausibly due to certain inductive biases in transformers that I think make them sort of predisposed to processing relations, essentially a kind of weaker version of the relational inductive biases in the models that I discussed. I think this also has an interesting connection to sort of classic cognitive models of analogy and what we think are the mechanisms of human analogical reasoning. But of course, there are still many major weaknesses. These systems have poor physical reasoning abilities. They have poor goal-directed planning, and the visual abilities of multimodal models are still extremely limited, especially in the case of multi-object vision. And so I think there are a number of directions that are going to be important for addressing these weaknesses. But some of the directions I'm most excited about are these object-centric processing methods, and especially, also other approaches for sort of learning more compositional factorized representations. And also, I think these methods for goal-directed planning that sort of break the problem down into different modular processes, I think is a promising approach that I'm really excited about. Okay, so that's all I have. So just say thanks to my collaborators in this work, and thanks very much for your attention.
We have a bit of time for questions, if there are some. Check online as well. Again?
Did one just come up there?
Hi, so I was wondering how the abstractor, was it a module or the model name? I forget.
The
That you
abstractor.
built on top of transformers, how that relates to early relation networks paper from DeepMind back in 2017. So is the difference mainly that we are using transformers now instead of LSTMs we were using before, or is there more fundamental difference here?
Yeah, so the main difference between really the three models that I talked about, ESBN, the co-RelNet from here, and the abstractor, is that the relations are being computed as inner products over some embeddings from the perceptual system. And so this is like a stronger inductive bias that I think almost kind of forces them to represent relations. Whereas in the case of the relation network, you have basically like an MLP.
Pairwise relations.
Exactly, yeah. So that can represent relations. It could also just pass on the object information if it wanted to. So it's just a stronger version of that inductive bias.
And can I ask a very basic question about object-centric networks? So I have a hard time understanding how we can model relationships between objects if we are reducing our representations to merely object level. So for example, in an image, I tend to think about images. I work on multimodal vision and language tasks. So in images, you have, let's say, a bunch of objects. When we have representations which are like coming from transformers or CNNs, we not only encode object information, but we also encode context information, right? And the layout, the arrangement of objects and all of that. But if I understand correctly, the premise of object-centric representation learning is that representations only contain object information, right? So if I have 5 objects, then I have 5 slots, and each slot is capturing information about each object. But at that point, I have lost the information about the arrangement of objects and also some context around the object. So if I take those slots and want to capture the relationship on top of that using a transformer, for example, how would I even be able to do that if I don't have the rest of the information available to me?
Right. Yeah, so I don't necessarily take object-centric processing to mean only having the object-focused representations. I think it totally makes sense to also include some sort of global representation, summary, context, gestalt of the image. I think the important part is just for there to be some representations that are focused on objects, rather than having the objects sort of distributed across multiple image patches in a kind of confusing way. So yeah.
Each slot would then be encoding, in addition to encoding an object, it would also be encoding other factors.
Or you could have a separate like summary vector, maybe that's just maybe an average of the scene, or yeah, I haven't thought about how to do it exactly, but it seems like there are ways to do it that don't necessarily break the overall object-centric paradigm, I think.
Thank you so much.
All right. I had a question about the modular architectures. One issue is you really want these intermediate boxes to be stochastic, as in like they can sample different things in their output based on the same input. There are many good reasons why this, there's ambiguity in the input and things like that. In interpreting the input, or what is a good plan, and so on. So it kind of breaks the usual end-to-end, gradient descent approach, and poses new problems because if you want to reason properly, maybe you need to marginalize over some of the things that are not. You can't sample everything. So I don't know if you've been thinking about these questions of uncertainty and latent quantities that such systems need to deal with.
Yeah, I have been thinking about exactly these questions. I don't think I have necessarily a fully formed answer, but this is basically, exactly what I'm working on now. I do think, yes, like the current version of this is very much not end-to-end, and I see that as a limitation. And I think figuring out how to build these sorts of systems in a way that can be optimized end-to-end is, I think, a really important goal. And yeah, dealing with, well, first of all, what are the objectives for these systems? How are we going to get them, if not through prompting, to fulfill these functions is a major open question. And then also there are optimization questions about how to deal with the fact that they're going to be sampling. Of course, there are methods for that, but yeah, this is an active area of focus for me.
I just want to mention that maybe the idea that we should train this whole thing with respect to one objective that is going to propagate everywhere is maybe not appropriate at all.
Of course.
So one way to think about, one way to think about this is people have been doing, and my group and others have been exploring how you can backprop through sort of stochastic computation. There are many approaches that are being used, but they will tend to focus on one solution. And really, if the right way to think about the problem involves somehow taking into account multiple modes, like multiple kinds of solutions, then these approaches will fail. But I don't think that means there's no way around. So if you bite the bullet that the objective function you're trying to optimize itself is not computable because it involves intractable sums, then there are still ways around. And the work that my group has been doing with generative flow networks, GFlow nets, is sort of suggestive of these kinds of approaches.
Yeah, no, I mean, these are all of the thoughts that I have as well. So yeah, I mean, basically one approach is don't try to train the whole thing end to end. Don't try to backprop through this whole procedure, but just come up with different objectives for these different modules. Right. It also seems like it could be a good approach. Sure.
Well, you still want the objective to depend on the overall behavior, right?
Yeah.
But you might not be able to do like pure gradient descent, and you need some other ways of thinking about how you get each module to improve. And you can look at how reinforcement learning works as a sort of guide for how this could work, right? You don't take the final reward and backprop through the whole chain of actions. Sometimes you can't because the actions are discrete, for example.
Yeah, hi, thank you for the talk. I had a question about this idea. So you talked about introducing inductive biases around object recognition, for example. And I wonder, the types of inductive biases that you were talking about were all sort of structural biases that you're introducing to the models. Mm-hmm. And when I think about tasks like vision and language tasks that exist, like vision question answering or mm-hmm. captioning type tasks, where we do have these sort of inductive biases that come from the linguistic data, we have models that seem to be able to learn to recognize these types of object level properties and reason about them. I'm thinking about like the Clever data set, for example, that does this. And so I wonder whether or not you have thoughts about maybe part of the issue with models like the GPT-4 that has visual capabilities being about how visual and language data is presented during training, and that those biases may actually still be possibly learned from input data, just the right input data.
So just to clarify the question, you're asking, is it a matter of how the multiple modalities are combined? And maybe if we figured out a different way to train the system that's more sort of deeply integrated, then we wouldn't need to have these architectural inductive biases. Right. Yeah, I mean, that seems like a possible outcome to me. I mean, I think, I would have predicted like 3 years ago that these relational inductive biases are probably like necessary to get these systems to process relations, but it turns out it doesn't need to be such a strong inductive bias to get relational processing. So it could be that the object-centric processing really just needs a better way of training the system. But I do think there are kind of fundamental constraints on the kinds of representations that you want and the kinds of limitations that impose, having to do with this binding problem. Basically, I think there's this sort of fundamental pressure to have shared representations. That's what's most useful for generalization. I think that these results are telling us that language models and multimodal models are developing these compositional representations to some extent, but that then basically imposes this binding problem. So I think you're going to have some way of basically sharing parameters in a way that's object focused in order to deal with this while still being able to have compositional representation. So there are different ways to approach that. You could imagine maybe a recurrent system, maybe developing this sort of sequential approach to focusing on objects in a way that doesn't require it to be trained, necessarily built into the architecture. That seems to be how human vision actually deals with it. But yeah, I think this is kind of a fundamental constraint that's going to have to be addressed one way or another.
I just wanted to follow up on that with the following thought/observation, which is that, and I think this was part of what you were getting at with your question, when we think about the data sets we're training on as well, it's remarkable how different they are from the data that a human trains on to some extent in terms of how much less important object-centric representations would be for these large multimodal models to solve the problems they're being asked to solve. Whereas, if you're a human and you're developing in the real world, then like objects are so critical for your ability to accomplish anything with your hands,
right,
and actually do stuff in the world. And so I do wonder if, even just more sort of like data that demands object-centric representations would go a long way. Not that it would be easy to get that data because it's not necessarily readily available on the internet, but
I think, I guess I would say that seems like it is absolutely necessary. Maybe not sufficient. Maybe we also need better architectures. But I mean, our visual systems don't develop to do static image captioning, right? Exactly. So there's going to have to be some sort of dynamic visual inputs. Totally agree.
I had a question regarding the modular network, the system, where you mentioned that you were planning on trying to fine-tune the different small networks with something else than in context learning. And I was wondering what kind of methods you had in mind, or if what you had in mind to fine-tune these models, because I think it's an issue in general, because the fine-tuning methods that we have are very expensive, and you need a lot of examples. And
Right. Okay, so I mean, what we found so far is that surprisingly, what I would consider to be a small amount of fine-tuning seems to be relatively effective in getting these modules to do the job that they're supposed to do. I mean, I think the fact that you can prompt them and get them to do it suggests they already can do it, basically, and they just have to be kind of pointed in the right direction. And so, it doesn't seem to require actually a lot of fine-tuning in this case. This is all just depending on the sort of raw capabilities of the pre-trained model in the first place. But how we're doing the fine-tuning, I mean, basically there's two approaches. One is, essentially sort of synthetic data approach of, trying to sort of bootstrap, based on sort of prompting a model, getting that to generate sort of examples, and then use that to fine-tune another version of the model. Again, this is not going to necessarily get it better than what it's already able to do in that domain, but just sort of develop a specialized version of it that you don't have to prompt in some task-specific way. And then beyond that, I mean, I'm really interested in thinking of more general purpose, principled objectives for training these systems, that relate to theories of goal-directed planning and reinforcement learning. There's lots of ideas that come from neuroscience here. So there's a brain region called the anterior cingulate cortex and prefrontal cortex that basically seems to be serving this monitoring role. And one way that people have characterized what that is doing is in terms of estimating the value of control. So it's basically saying, is my default response pretty good, or do I need to sort of think about this more? And you can formalize that using essentially reinforcement learning formalism. And so those are the sorts of objectives I'd really like to think about for these systems, rather than just having a sort of synthetic kind of ad hoc data approach. But yeah.
Thank you.
Thanks. That was a fantastic talk. I've got a bit of a meta question. Did you try asking some of the large language models the question to try to come up with a reasoning task? And maybe multiple reasoning tasks, and explain why some would be more targeted towards some type of reasoning approach or others. In other words, looking into its ability to take a step back and do some meta cognitive processes on that.
I haven't tried that. That would be super interesting. One thing that people have done in work in the lab that I was recently working in is asking them to propose metaphors and sort of metaphorical tasks. And they actually surprisingly seem to be able to do that in a way that human raters rate as being better than human-generated metaphors, which is somewhat surprising. But yeah, I think it'd be super interesting to see the kind of tasks that they come up with. I guess for the purposes of evaluating their reasoning abilities, really the goal was to come up with tasks that I came up with that I know they wouldn't have seen before, right? And so that would kind of go against that particular goal. But yeah, I think that would definitely be interesting to look at.
All right, so we'll officially end the talk and thank Taylor again.
Thanks.
That was great.